I want to say, first of all, what an honor it is to be here presenting at the Princeton Combustion Institute Summer School. Ever since I was a PhD student, I graduated in '95 at University of Michigan. I've always revered the Princeton Combustion program, as I see it as the best in the world. And you can tell from the faculty here who not only have won all the awards, but have the awards now named after them. And so it's such an honor to be here. So today I'm going to start the first of 6 presentations on fire research, and especially experimental fire research. But ironically, the first set of slides is about analysis, about some fluid mechanic analysis of fire hoses. So a little bit about me. I grew up in Amherst, Massachusetts. My father was an engineering professor, but I went to Cornell for my bachelor's degree and then did a master's back at University of Massachusetts and my PhD in Ann Arbor in aerospace engineering. My PhD was sponsored by NASA, and it was a natural fit for me to go to Cleveland, to NASA Glenn Research Center after that, and do microgravity combustion research. And then since 2004, I've been at University of Maryland in the Department of Fire Protection Engineering. So I do want to acknowledge my advisor, Gerard Faith. He passed away in 2005. My supervisor at NASA Glenn, David Urban, graduate of this program at Princeton. Richard Axelbaum, also a Princeton grad from Washington University, and Jim Quinteri at University of Maryland. And I see these 4 people really as my main mentors in my career from the PhD and onward. So for those of you who are just in combustion, I want to give you, and that's my PhD was in combustion. I still do about half of my research in combustion. Want to give you a little bit of an understanding of the differences between combustion and fire research. And as I do this, I also want to impress upon you some of the excitement of working in the realm of fire research and how needed it is for people with outstanding combustion skills to start to apply some of those methods to fire problems. And there's still a lot of low-hanging fruit in the fire community to look at problems with a lens of a combustion background. So this table has 2 columns, some aspects of combustion research and some aspects of fire research. And the first thing is that you'll notice the journals are a little bit different in fire versus combustion. So in combustion, everyone publishes in Combustion and Flame and Proceedings of Combustion Institute. In fire, they often do publish in PCI, but also in the fire journals, journals with names like Fire, Fire Safety Journal, and Fire Technology. So that is a big distinction right there. But of course, I think the 4th item down here, the applications, is really where you see the biggest difference between fire and combustion. So in combustion, the applications are for engines and burners, so propulsion and engines. And in fire, the application always is for fire safety. But there's a lot of overlap in these 2 disciplines. The fire size, normally it's often small in combustion, but some large fires. Usually in combustion, if you're looking at a combustion application, you want your engine to be as small as you can, or your burner. No sense making an engine larger than it needs to be. In fire, you don't really control the size. You also want the fire to be small, but generally the fires are large in fire applications. Combustion problems often are optically thin because of these small flames, and maybe flames where you're trying to avoid production of soot. You often have optically thin. In almost all fire problems, you have optically thick viewing. And this makes it problematic to do a lot of laser and camera diagnostics that you could otherwise do in combustion. Almost all fires are turbulent because the scales are large, whereas in combustion, there's a lot of advances that have happened using laminar flames. Computations are different. Fire is usually large eddy simulation, whereas combustion problems often are going to DNS. And then diagnostics and chemistry models are generally more advanced in combustion research than in fire research. So on this slide, I show a bit of the growth of fire research, and you can see that the number of papers is increasing, at least at the Combustion Symposium. And it used to be about 10% of the papers at the Combustion Symposium. This is just 10 years ago. 10% of the papers were fire papers. And at the last symposium was 16%. So the fire problems aren't going away. Combustion, we may see a little bit of a decrease in combustion research as the automakers especially are looking to transition to electric vehicles. I think aircraft and shipping, large ocean-going vessels will be using combustion for the next 30 years. But as far as highway vehicles, we are seeing a transition toward electric vehicles. With that, I want to turn my attention now to a fluid mechanics problem. And when I was an undergraduate, my favorite class at Cornell was fluid mechanics. And we had Professor Leibovich. He didn't bring any notes in the class. He did everything from the top of his head, very advanced math, but in a way that everybody could understand. And ever since I took his class, I always felt like fluid mechanics, that was my passion. It was the first time I had a true passion. And one thing I love about combustion is there's a lot, and fire, there's a lot of room to look at the fluid mechanics. And when I taught fluid mechanics the second time, I wanted to assign some fluids problems that are pertinent to fire protection. And so I was interested in the fire hose and the fire spray problem. And when I looked in some of the textbooks, the problem hadn't been solved. And where it had been solved, I found it to be rather misleading. So with some undergraduates who are acknowledged here, especially Selena Chin, we looked at this problem, and from very fundamental, easy fluid mechanics equations, conservation of momentum in an integral form, we believe we'd actually have solved the problem in a way that can be helpful to firefighters. The first thing I want you to notice about this image is that those firefighters, they're pushing hard forward on this hose. Now, this is larger than a normal attack line you would use inside a residence, but yet you see the backup person has a strap over their shoulder hooked onto the hose, leaning forward, pulling on that strap, and pushing on the shoulder of the front person. And the front person has two big handles on that nozzle, and they're both bracing themselves and leaning forward, and probably pushing, with a good deal of force on that nozzle. So this is the problem I want to introduce next. And by the way, we published this in 2017 with Grunda Jomas, another graduate of the Princeton Combustion program, a student of ed law. So let's start with a couple of definitions. Where this is an examination of nozzle reaction forces. So how hard you have to push on that nozzle to hold it in place while it's spraying. And you can see the image at the right here. This is someone having a good time on a lake, on vacation, something that's powered by a big pump and that yellow hose that's able to lift them into the air and sport around and kind of like a jetpack. So this is the nozzle reaction or the kickback. It's the force that's needed to hold the nozzle in a fixed position. And the other quantity we can solve for with this problem is called the hose tension. So the hoses are under tension, it's high pressure water, and the hose needs to be able to withstand those tension forces. So the main motivation here is for firefighter safety. But the secondary motivation too is to improve effective firefighting. If the firefighters aren't able to do calculations and estimate the forces that they're applying, then they may be either holding too much force or not putting enough water on the fires. So we think with a better understanding, hopefully they can improve both, reduce the injuries and improve the firefighting. The injuries are significant in the United States. About 14,000 injuries per year are associated with charged hose lines. Reaction forces are also important for other areas like agriculture, spraying crops, pressure washers, and firefighting drones even. So here's a little bit of a background. Many people have looked at this problem, including Mach, Prantl, and Richard Feynman. When I was young, I read a book by Richard Feynman, and he said, if you look at a backyard sprinkler, the old kind that used to spin around and as it sprayed the water, and he said one thing he loved about his job advising PhD students is that no matter what measurement that student might make in the laboratory, he could explain it. And he said that if a student were to measure the spinning water hose submerged underwater, and whether it's spun the same direction as in air or the opposite direction, that he would be able to explain it. And I was always captivated by that, and it's interesting that it's been a problem that's followed me. What do people think? Has anybody ever thought about that? Do you think it would spin in the same direction, opposite direction, or not spin at all? Anybody have an intuition about it? Again, from a general phenomenological perspective, Richard Feynman said that either way could be explained with rudimentary physics. Any intuition? I think it won't spin. Might spin a little bit, but it won't spin a lot. And the reason is that when you sneeze, the turbulence is felt many meters away. But when you inhale very quickly, the gas comes from all directions. It doesn't jet out. It doesn't jet back into your mouth. So when you use this in your backyard, it spins because you have this jetting. But if it were submerged, you wouldn't have any jetting. The water would come in from all directions, and I believe it wouldn't turn. Another example is shown here, a water carnival game. So I think we've all played this. What you do is you take this water hose and you spray it in the clown's mouth. It pushes the mouth back, and that allows air to fill up the balloon. And the first balloon that bursts wins the prize. And what I want to impress upon you is that you have to push forward on this water gun, and that the same amount of force that you apply to the gun is the force that the clown feels on the back of their mouth. And that's assuming that the water drips straight down. And it all makes sense intuitively, but this hadn't been shown before with a fundamental conservation of equation solution. Okay, other people have looked at it before. Lautrip looked at it and found rho v squared A was the reaction force. The NFPA handbook has these expressions, but no justification. There's no paper trail for them, and they're quite approximate. So we were the first ones really to try to solve this problem from a fluid mechanics standpoint. Now, I did, as I was assigning homeworks for this class and thinking about what kind of midterm and final exam questions I could ask, I looked in other books to see what others were doing. And here are two textbooks that had, I think, rather misleading solutions of the water hose problem. So on the left, this is Nazarenko, and he solved the force on a hose. But I think everyone knows from playing in their backyard that if you stand on the end of the hose and spray water, the hose doesn't go flopping all around. There's no force on the hose. So applying the force to the hose really didn't make any sense. Firefighters, they wouldn't hold the hose. It would probably hit them or somebody else in the head. You need to anchor. You need a reaction force at the end, at the solid nozzle. White is a textbook many of us may have used here. It's a very famous, widely used textbook. And White calls it a fire hose, but actually they're solving the problem of a converging nozzle bolted onto a solid pipe. So that really it's solving an interesting problem, but it's not the problem that they set out to solve. And then, perhaps worst of all, in 2015, some researchers actually published a paper that said, is a backward force a myth? And the hypothesis of their paper is that if you hold the hose straight enough, if you try to have a nice straight hose, that you won't have any reaction force at all. And I have a problem with this because firefighters, they're a little bit superstitious. I've had firefighting training. This is at Maryland Fire and Rescue Institute, where they train all the state firefighters, where they say that in the northern hemisphere, the Coriolis force spins the water in the hose in the, I don't remember, clockwise direction. Because of the Coriolis force, you have to attack the fire in the opposite direction, and the fire will go out better. So of all the things the firefighters have to worry about, they're thinking about some fictitious Coriolis effect. And if that's not bad enough, here you have researchers, okay? These are PhD researchers at universities saying that, well, don't worry about the Coriolis effect, but just hold your hose nice and straight. And what we find is that you can't hold a hose straight enough. There's no such thing as a perfectly straight hose. And even if you could, it would have the same force. So after seeing this, I was really motivated to see if I could solve the problem. Of course, it didn't happen during the class, but soon after. Here's a picture of a bunch of kids at a birthday party. The kid in the front's leaning forward. You can see one leg is pushing back. So even though it's a very low pressure, there's a good force. You feel that. I think this is just before she sprayed all of her friends. And what I want to impress upon you is that that person is pushing forward on the hose. And as she angles it around, there's no way for that information to propagate back to the fire pumper. So any force that she applies on that hose as it's spraying, a forward force, is the same as the force when that water impacts the ground. And that is just the jet momentum flow rate. So as a phenomenological approach, you can jump right to the right answer, that the force that she's applying in all firefighters to the hose, no matter how much it's bent, is the jet momentum flow rate. But you can't really publish a paper and say phenomenologically put this image in there, but we do solve it with the conservation of momentum. Okay, so first we needed to solve for the hose tension. So the hose has a hoop stress. All the hose designers, that's very easy. You know the pressure, and so you know how strong to make the knitting, the tissue fabric of the hose. But the hose manufacturers, before this, they didn't know what was the tension force on that hose. But we were able to solve it just with integral conservation of momentum. Really, this is a homework problem for a sophomore or junior. And for any angle of bend, if you look at the normal vectors and the velocity, you have a tension on two ends of this control volume. And you can solve for the tension with the final result there. And the key takeaway here is that no matter what the bend is, whether it's 0 degrees or 90 degrees, the amount of the hose tension is independent of that hose angle. So once we have the hose tension, now we can consider a metal nozzle. And we consider two here, one that's straight on the left and one that's bent. And in both cases now, the hose is actually pulling on the nozzle. And so the firefighter has to push forward with this force F to overcome that hose tension. But you, of course, also have the pressure forces and the momentum change there. But it's really, again, a simple type of homework problem for an undergraduate student to solve for the reaction force. And there you see it as the last equation on this slide. The reaction force here is rho q squared over the area of the jet. And in other words, the nozzle reaction is the jet momentum flow rate. So whatever force the kid at the carnival is pushing on their squirt gun is the same force on the clown. If you ever see police with protesters, it looks like the protesters, I'm sure it's very painful to get hit by a water cannon, but the total force on the protester is the same as the police are exerting on the water cannons. And in both cases, the nozzle reaction is the jet momentum flow rate. Now, this isn't to say that firefighters have lots of tricks. They can put their knee on the hose. They can brace it. They can bend it and brace it against a table or some fixed object. They always work with two people. So there are ways to overcome these nozzle reactions. But if we can find ways to reduce them or help them understand them, maybe we can have fewer injuries and more effective firefighting with water. So this is a plot of some of those relationships between the reaction force on the y-axis and the volumetric flow rate on the x-axis. And the key thing from these equations is that the reaction force is proportional to the flow rate squared. So if you double that flow rate by opening that bail valve, then you're going to have 4 times the reaction force. And these can easily get up to the weight of a firefighter. The reaction force also decreases with increasing diameter. So one thing that I'm trying to get across to firefighters is try to work with a larger size nozzle. Don't work with these 12 millimeter nozzles. Go to the 25 millimeter nozzle, and you'll have 1/4 the reaction force at the same flow rate. Now, that gets to be problematic because if they run pressures that are too low, as soon as they go through a door, the hose kinks. Or if they go upstairs, they don't get enough pressure. So there needs to be some more clever ways to do that we're also looking at. National Fire Protection Association, they do require the initial line to have 400 liters per minute, and that's with 2 people on it. And if you look at that, the first vertical dashed line here, if you're working with the normal 12 millimeter spray nozzle and you're flowing that amount, the reaction force is 334 newtons. Now for me, unfortunately, I work in metric, but I still think in pounds. That's about half my weight, about 75 pounds. So imagine you're a firefighter, and maybe your backup person is distracted or on the radio, took their hands off the hose, and you open the hose, you're ready to flow, and its reaction force is half of your weight. And not only that, but another, maybe 1/3 of your weight is the scuba tank, the helmet, the boots, the turnout gear, maybe you're wet. So you're carrying around all this weight, and you've got big, heavy gloves on, and now you're almost getting thrown off your feet on a slippery floor. So I can see why they would be very concerned about these reaction forces and eager to drop them. And the best way for them to drop the reaction forces is to go to bigger diameters. As you can see here, move to the right. Those are all parabolic curves, but move to a bigger diameter and a lower pressure. By the way, please stop me anytime. We started a few minutes late, but there's always time and room and encouragement for questions. Also, I want to say that from my slides, the ones that are posted have too many slides in the 7 days since I uploaded those. I've reduced a lot of slides. So if you're trying to follow along on your computers, I'm sorry if it's not a one-for-one. All the slides will be there, but you may have to skip through some of the unnecessary slides. So now we'll introduce Bernoulli equations. So far, all we've assumed really is the water's incompressible and that it's the conservation of momentum. But sometimes you know the pressure, but you don't know either the flow rate or the area. And especially as you saw in that picture of the girl at the birthday party spraying a fog nozzle, this is a nozzle with a whole bunch of little holes, and it would be hard to know what is the area of that jet discharge. So in that case, we can introduce the Bernoulli equation, which we all have studied as sophomores and juniors in engineering school. And then we get two different reaction expressions. The one on the left, which is very useful if you don't know the flow rate. So if you know your pressure and you know your areas, the area of the hose and the area of the spray, very useful expression. Or on the right, this expression for the reaction rate, which is very useful if you don't know the area, but you know your flow rate and your pressure. And by the way, most pumpers, this is the people operating the truck outside, they have a radio, and they can see the pressure on the pumper, and often the pumpers also can measure the flow rates. So really, if you want to have, ideally, the firefighters, they want a high Q, and they want a low reaction rate. And so the reaction force, the best way for them to get that is to have a big nozzle and a low pressure. And as I mentioned, that low pressure gets problematic if you go upstairs or around a corner. So there is an equation in NFPA, and this is shown here. Some of the graphics are a little bit garbled, but I'll tell you that on the y-axis, this is called NFPA reaction versus the diameter ratio, the hose diameter divided by the jet diameter. And the NFPA, they give these expressions as shown here on the top line that have no units. So I rally against these kind of expressions because they only work if your pressures in kilopascals and your diameters in millimeters, the flow rates in liters per minute. But that's what firefighters need. The firefighters do have to do math, and they're not very good at converting units. So the equations that they work with are equations that look like this, that to us kind of makes my stomach turn. But it does work reasonably well as long as as long as you're at a low D2 over D1, so a small nozzle and a big hose. But what we found is that most firefighters, they work out to the right of this curve, sort of in the middle, past the knee bend, in the region of 0.5 to 0.8 on the x-axis. And here then what it means is that the equations that they're using are under-predicting the reaction forces almost by a factor of 2. And when I've spoken to firefighters about this, what they say is, yeah, we do that math, but then we just multiply by 2 every time to make sure that we're safe. And it's really a shame. So they're being told, Coriolis to force in your hose. They're being told, hold your hose rate. And they're also being told, you're not as strong as you think you are because you should be able to handle this. This should be an easy force. But actually, the force they're calculating is half of what they're really feeling. And so this is an unfortunate situation that I hope, as we get information out about this, can improve their lives. And ours, if we have a fire in our house, I want them to be able to put the maximum amount of water on it without getting blown off their feet. So there aren't very many measurements of this. It's a measurement that I'm very eager to try. I think this year I have a group of undergraduates who are going to start doing some of these measurements, but there are no measurements of reaction forces in the peer review literature. What I found is images like this, someone at a firehouse who used a fishing scale and a couple of webbing straps and opened the hose and measured the forces. And they did test 1 and test 2. That's the best data that we could find, and it did reasonably well agree with our measurements. So that was encouraging that we're going in the right direction. And I look forward to having better predictions in the future. Yes?
So, one of the objectives of firefighting shouldn't be like how far your nozzle can spray. The only objective I see is like the flow rate, and to decrease the reactive forces, say go increase the area, but like is the range not one of the objectives?
Excellent point. So for those who may not have heard or for the video, what I've said so far a few times is that if you want to reduce the reaction force and have a high flow rate, just reduce your pressure it would be easy on your feet, and you get a lot of water on the fire. But you're exactly right. There's a price for that. First, your hose can kink, and second, it's not going to spray to the back of this room. And so there needs to be some common sense about this. What we're hoping for is maybe some kind of a device on the nozzle itself where the firefighter can actually adjust the pressure and the flow rate. So if you're in a large room like this, you do need a lot of pressure. You can accept a lower volumetric flow rate. Crank with the pressure, you get the flames that are back there. But a lot of times for residence fires, the rooms are small, at least where I live in Maryland, small colonials. You really don't need, they typically run with at least 50 PSI, and you don't need that kind of a pressure in a small place. Now, if you're outside and the spray is anchored to the truck and you're fighting a tall building, of course you want high pressure, and you're probably not too worried about the reaction forces. I'm more interested in the interior firefighting. But very good point, thank you. Okay, so what I want to talk next about is kind of making a transition to burning and real fires, and of course my passion, which is the experimental methods. This was just a fun little toy problem for fluid mechanics. And so for the next few slides, I want to go over what I see as some of the grand challenges that are facing the fire community. And I hope in this that those of you who are doing combustion who haven't had much exposure to it yet, and it makes sense, if you're a PhD student, you don't want to work on 3 or 4 problems. One's about all that most people are happy to handle as a PhD student. But maybe as you graduate and look for other jobs, think about how you might contribute to some of these fire problems. And while I think all combustion research helps society and helps the environment, you're reducing the use of fossil fuels, you're reducing pollutants and making, using less metal to make cars and aircraft. Those are all good things for society. Attacking the fire problem also is very good for society. So I've picked, I think, about 6 of the grand challenges that I want to talk about next. And as you maybe could anticipate, the one that always comes first is wildfires. So there are 2 types of wildfires. There are wildland fires that are like forest fires back in the woods where nobody lives. And then the second category of wildfires are called WUI fires, or wildland urban interface fires. And these are fires where houses that are embedded in the forest actually burn. And the WUI fires are a big problem because the insurance losses are greater, people are displaced, people are more likely to be injured by the fire, and often the firefighters can't just let it burn because you have the residents saying, hey, that fire is approaching my house, get your truck down there and protect my house. So the WUI fires have really been a big focus of wildfire research and application. So the problem is huge, and it's getting worse every year. In the United States, the cost is about $1 billion per year, but we do have fires that are much larger than that. In 2018, the Camp Fire caused $9 billion. This is one fire, $9 billion in loss. So it's really a tremendous problem. If you can think of some great way to reduce those losses, NSF will give you a grant in a heartbeat. If you tell them, I can make that $9 billion, $4 billion, just give me $300,000, of course they're going to do it. There's a great leverage and a great benefit to any kind of good idea in fire research to help with fire prevention and response. So fires are only increasing in the WUI and the wildlands because of climate change. And ironically, the climate changes, things are hotter and drier. Those hot and dry days, the fuel dries out, and then the biomass burns easier. Once it burns now, it creates more climate change because the CO2 goes into the atmosphere, and now you no longer have trees, but you may have just ash and charred remains. So it's a problem that's feeding on itself. We're seeing huge fires in Canada now most summers, and these are affecting the air quality here and all through the United States. There's some video links here, but I'm not going to play them today. If you like, of course, you can pick them up from the PDFs. So some people would say, well, wildland fires, this is just a natural phenomenon. It's like a hurricane, tornado, lightning strike. What are you going to do? How are you going to protect against a lightning strike? And I think that in the fire research community, we've come to realize that there are things that we can do. And first and foremost, we need to study the problem and understand how the fire dynamics behaves. We need to have better computer models, because these models can help with maybe having a municipality tell people, well, you're not allowed to build in that canyon. That's a high fire-prone area. And also improving the codes and standards. And we've seen that already a lot with codes and standards. In many of these WUI fires, the houses that were up to code, and the up to code often doesn't mean they need to spend that much money, they were twice as likely to survive. Now, the other side of that means that if your house is up to code and your neighbor's isn't, it's more likely to burn and spread into yours. So I imagine that in these communities, there's some tension among the neighbors and peer pressure to try to lift things up. The kind of things that people can do to improve the code compliance is as simple as removing the brush around your house, removing the mulch, not having outdoor decks. I know everyone loves the outdoor decks, but those are really a major source of loss in fires. And whether they're made out of Trex, plastic, or wood, they're really a magnet for starting the house on fire. If your deck catches fire and there's no fire service to protect you, your house will burn down. And another thing is like vents, wired mesh vents on the attic vents. So instead of allowing embers to blow into your attic and start a fire there, it's very simple. Just have these wire screens that prevent that. All kinds of better understanding is better for the fuels, which fuels are more flammable, the fire weather, the history of fire in that region, and the aspect, whether it's facing north, south, east, or west, and how steep it is. All these things are important to fire and fire spread rates, but not fully understood yet. And we need better risk analysis and, as I mentioned, better fire models. And ideally, what you'd like is for the fire incident commanders to have a laptop in their vehicle that's running some kind of a LES, large eddy simulation model, with weather and with the current fire conditions, and then able to predict where they need to exert their resources and where they need to evacuate. So I think in the fire community, about half of the researchers now are targeted on this problem on wildfires. But it's not the only one, and let me express and talk about some of the other grand challenges. This one's about residential fires. And of course, there are lots of residential fires. The last thing you want to see is a house like this going up in flames. But in the United States, in 23, we had 330,000 residential fires. Now, many of these were very small. You know, someone burned some popcorn and called the fire service. But some were complete losses, like may happen with this fire here. The deaths are large, about 3,000 a year, and $11 billion in property damage. So the property damage is greater than the wildland fires, although one single wildland fire can get up to this $11 billion number. For your own benefit, not in terms of research, keep in mind that the main cause of fires is cooking fires, but also heating fires or significant smoking, and electrical fires. Now, electrical fires typically are the thing that gets blamed. When they can't find anything else, they rule out arson, they rule out cooking, they rule out the furnace system. Then they decide, oh, it had to be an electrical fire. There's electricity everywhere, and for the incident investigators, that usually gets blamed if nothing else can be found. Residential fires are a problem in the United States because we have a large volunteer service, and we have 27,000 fire departments. People from Europe just found this astonishing. My wife is French, and in France, there's one fire service. In the United States, we have 27,000. And as I mentioned, not only the firefighters suffer from pseudoscience, but the fire investigators. I've read reports where fire investigators say, you know, look at the door, look at the carpet near the door. It's all charred and burned. It burned right near the door. Someone must have poured accelerant near the door, and it's an arson fire. But that was wrong. The door is where the air is rushing in. So the room is burning and it's hot, and the carpet there is hot, and it's the only place where there's air. It's under-ventilated fire. And of course, then, the near doors and near windows is where you see a lot of burning. So we're starting in our department to do a lot of research and test fires to learn about these investigations and try to make them more scientific. So what can be done? Of course, we need better fire retardants. Now in the United States, all those chemical fire retardants that we had in children's sleepwear are being phased out. They're too toxic. And so they're looking at other ways to protect that, especially with charring, ways to make the clothing or the carpet to char, kind of like wood chars when it burns, instead of having gas phase retardants. We need better smoke detectors. In my house, it's a 3-bedroom house. I think I have 6 smoke detectors. And that's sort of the minimum that NFPA says. Every bedroom's got to have one outside every bedroom. You've got to have 2 CO detectors and 1 on every level. And not only that, but then every time you change your clock, you're going to change all those batteries. So we definitely need better smoke detectors. They're starting to come, but we need more. And if you only remember one thing today, please remember you should never go to sleep in a room without a smoke detector. At least in the United States, I think our construction, there's a lot of wood construction, and you're vulnerable without smoke detectors. I would love to see more emergency response robots and drones. I have a slide about that coming up next. And of course, for residential fires, we need better fire modeling like FDS, that's a NIST, Large Eddy Simulators system, and fire foam. The next one, and this is one of the topics I'll talk about tomorrow afternoon, my last of 6 presentations, is battery energy storage systems, BESS. And as you know, the demand for energy storage is going up and up. Everyone wants a better performing phone, better performing car, a better performing data center. And all these things are encouraging the use of lithium batteries. And of course, AI now with ChatGPT, their data centers are huge users of electricity. And if that electricity supply should get cut, they need to have lots of batteries inside the data center, even inside the racks, to protect them. The fires can arise from the lithium batteries, from all types of things, damage or material defects. And the fires are very hard to suppress. I've seen firefighters that say, oh, if there's electric vehicle fire, all you can do is throw that vehicle into a swimming pool, because almost no amount of water that you spray on the fire will get to the battery. Of course, the car's designed to shed water, and when it rains, you don't want the electric system to get wet. So of course it sheds the water when the firefighters attack it. The 2 images on the bottom here are from this year. It's at Moss Landing. This is in California. It was the world's largest electric storage system, 750 megawatts. And the idea here is that, if at night you can get energy from the nuclear plants or maybe from wind power and charge up these batteries, and then in the daytime when people are demanding a lot of electricity, you supply that. But this caught fire. Hasn't really been determined how it burned, and it caused extensive damage. So the emissions are very toxic. You get a lot of HF, cobalt, nickel, copper, manganese, all kinds of things that you don't want to breathe, and all kinds of things that get in the drinking water, get into the soil. And it's not just in the air. So I think we're going to see more and more of these systems, and we're going to see more and more of them burning. So what can be done? Hopefully we can design safer battery chemistry, but in a time when we want our cell phone to run for 8 hours, or our laptop to run for 5 hours, the energy density is going to need to stay as it is or increase. And once you charge up a battery like that, if something goes wrong, it's a lot of energy that comes out very quickly and can start a fire. More firewalls between the batteries can help, so that if one battery has thermal runaway, you have some protection, some space, or some insulation to protect against the propagation. And of course, better prevention, detection, and suppression. There's the last 2 images here on the right is the data center rack density versus the year. And you can see that this is just climbing exponentially. And what's happening here is now, as we're going to artificial intelligence, the amount of computing power is increasing, but the space it takes is decreasing. And I have a friend who visited a data center that used to be a traditional data center. It was full of computers and loud and noisy in there. And when he went back a few years later, it had shrunk to about 1/4 of the size. And yet it was using far more energy, because now these are graphics processors doing artificial intelligence. So what's happening now? with these data centers is that they're getting smaller and using more electricity. And for that, they need to protect against electrical outage with larger batteries. And if you have a fire there, that can be $1 billion loss right away. Okay, on to the next grand challenge. This is smart firefighting. And if you look at the two images on the left, today we use a pumper truck and a tank, and in the 1800s we used pumper trucks and tanks. Firefighting is a funny business because you meet firefighters who are like, yeah, I'm the 6th generation of firefighters. It's kind of like I did a lot of work with candles, the same kind of thing. You know, my great-great-grandmother started a candle company. So if you talk to these firefighters, they're like, yeah, it's the same way we've been fighting fires all this time. Just drive to the fire and spray water on it. And why aren't we getting smarter? Why don't we have smarter buildings that can tell the firefighters whether maybe there are people involved or where the fires are a little bit better? And so I think we're going to see more of that coming. When I interviewed for my job at University of Maryland, the department chair told me that. He's like, there's a lot of opportunity in firefighting. These people, who are in the industry haven't really applied the advanced science and math that we've seen in a lot of other engineering disciplines. And I think that's true. And luckily now I think we're starting to see this with firefighting drones, firefighting detectors, rooftop and satellite type of watching for fires. And here is some kind of a firefighting robot. So why should we send firefighters into a burning building to risk their life? It's not that rare for a ceiling to collapse. And if firefighters are in there when that happens, it's difficult to survive. So I think smart firefighting is another good application for research. This one is relatively new. These are 2 examples of facade fires. Most building construction isn't like these beautiful buildings we see all around campus, stone walls that aren't going to burn no matter what. This is beautiful. I love the architecture here. I just walk around and admire it. And you have to admire it too for its fire retardancy. But most construction now, and especially in high rises, is going to this aluminum facade. And the idea is that you put aluminum sheets up, and they can be any color, and they look really nice. They're not expensive. And then behind the sheet, you have some kind of a polymer, like styrene or polyethylene, some type of a foam to provide insulation and also noise insulation. But in several of these fires, as you can see here, the foam behind this aluminum has caught fire. It actually heats up the aluminum enough that it will melt and drip, and it also will start burning. And many people have died, and there have been huge losses. So these are facade fires. It's a big area of research. Should these be allowed? What kind of materials are safe? And how do we fight them? Of course, no fire hose can reach up to such a high building as this. The one on the right is the famous Grenfell Tower fire in London, where I believe 80 people perished. Really a great tragedy. So what can be done for this? Codes and standards need to be improved. How can you take a piece of this facade in a laboratory and do a test that can tell you about how it will burn on a skyscraper building? And there's a lot of research going on in this. And do we really need to retrofit all the buildings that are designed like Grenfell? Do we need to go back and rip off that siding and put on a new facade? And then this is the last slide. This is about informal settlements. While we're looking at improving fire protection for the $10 million estate in Hollywood Hills, and I'm all for that. Let's make that house as safe as we can. Let's also think about those in the global south who aren't as fortunate, who may live in an informal settlement like the 2 that are shown here. And it's a difficult problem because it's not only a fire problem and a technical problem. There may be interesting solutions, but it's also a political problem and a problem where there isn't a good water supply, there isn't a fire service. And these are really hard problems. On the right there is a fire that started in an informal settlement, and people lose everything when this happens. And there's nobody to call to come put out your fire. So people are looking at this problem, especially Europe is very involved. University of Edinburgh is very involved in this. And they're looking at improved detection, notification, egress systems. And the thing about this is that you may install beautiful detectors and intercommunicating detectors in these buildings, but then they need to recharge the batteries. They need to change the batteries. Someone needs to maintain them, and that step often is missing. And perhaps better prevention and less fire spread. But of course, as I mentioned, it is a political issue that needs to be attacked from multiple angles. With that, I've gotten us almost back on time. If there are any questions, I'll take them now, or we can have a 15-minute break and come back at 15:15. Yes?
Okay, when you were giving the things to do in the code compliance, you had to remove the brush and then no outdoor what?
No deck, no patio, no balcony,
Oh, okay.
no wood structure outside of your house.
Okay, thank you.
Thank you. Okay, thanks everybody. I'll see you in a few minutes.